Hi, welcome to Futureproof for our Planet, our Sustainability Master Series. I'm Esther, I'm a second year physics student and I'll be your host. Today's session will be a chemistry session with Giacomo and Aaron.
Hi.
And they'll be going over how photochemistry can help us become more sustainable. Today's session we actually have a special guest as well. We have Professor Jen O'Brien, who's our sustainability leader at our university. You want to say hi?
Hi everyone.
So we're going to watch a video from Giacomo and Aaron, and then afterwards you guys can put in questions for the Q&A for both of them, and you can also have questions for Jen about general sustainability questions.
Hello, my name is Dr. Aaron Trowbridge and I'm a lecturer here at the University of Manchester. And my research focuses on using visible light to drive new and exciting chemical transformations. For hundreds of years, chemists have used heat to drive chemical reactions. And there's a good reason for this. Just like baking a cake at home, you need to put in some energy to get those molecules to crash into one another with enough oomph to react. The problem is, when you heat up your reaction, it's quite indiscriminate. Everything in your flask is heated up to the same temperature, and so it lacks that chemical precision. As synthetic chemists, we aspire to create a toolbox of reactions that target different parts of a complex molecule selectively, creating a sort of molecular tweezer to stitch in, chop out, and move around certain atoms, leaving the rest of the molecule intact. And this point is key. Making molecules from scratch is an extremely time-consuming, costly, and wasteful process. Many of the cutting-edge drugs coming out this year will have been as a result of a multi-billion-dollar, decade-long campaign where the nature and location of every single atom within that final structure has been painstakingly optimized, and each time making a whole new molecule from scratch. Just think of the savings and benefits that using just one molecule instead of hundreds to access all of this chemical space would bring. That's using scientific innovation to drive sustainability on a global scale. So you may ask, why don't these reactions exist already? Chemistry's been around for hundreds of years. The answer is that delivering such site selectivity in complex systems is a near impossible task. What we need is a way to store up all of this energy and deliver it in a highly targeted way. And of course, for inspiration, we turn to nature for help. Every year, plants and trees across the globe turn more than 100 billion tons of carbon dioxide into carbohydrates. And it does this remarkable transformation using light from the sun, or more technically, photons. And this is all made possible by the fact that the photons that make up visible light contain an enormous amount of energy. In fact, it's the same as needing to heat up your flask to about 600 degrees Celsius. So a sensible question is, why aren't we all being cooked alive? The answer is actually pretty simple. The energy's there, but we don't have very much in our bodies that absorbs it. So instead, we just get a nice tan. The same philosophy is also true of chemical reactions. Most bits of the molecules that make up pharmaceuticals don't interact with visible light at all. Over millennia, plants have developed highly complex machinery that can take these photons and turn them into chemical energy, but more importantly, it delivers this energy selectively to specific molecules. One of the most crucial bits of kit is the chlorophyll, the green pigment. This acts as an antenna to absorb the light. The problem is that this biological power station, as you would expect, is highly specialized for photosynthesis, not for chemical reactions needed to activate drugs in a laboratory. So chemists have come up with their own solutions to this problem. Some of the most widespread antennae, known as photocatalysts, rely on rare earth metals lurking at the heart of the periodic table. Foremost among these are complexes of a metal called iridium, named after the Greek goddess of the rainbow due to its varied colours of its compounds. It is, however, one of the rarest and most expensive metals on Earth, prized for its chemical resistance, its presence thought to be solely as a result of asteroid impacts. In effect, we are performing chemical reactions with moon dust. The breadth of these emerging visible light-mediated transformations is truly remarkable, allowing chemists to do reactions thought impossible just a decade ago. In our group, we are looking for new ways to direct this energy towards new and exciting transformations. One direction we are pursuing now involves moving specific groups around the outside of a molecule from one atom to the next, designing these important molecular tweezers. Current methods to do this are very challenging and time-consuming, like trying to modify a Lego set with oven gloves on. But we're able to make the problem a lot easier by installing reactive groups that pick up the energy selectively, effectively making the Lego blocks much bigger. But if we are to benefit from this step change in synthetic chemistry in the decades ahead, we must adapt and explore new and sustainable systems. Particularly prized are those that operate at the other end of the spectrum using red light instead of blue. This is particularly important for industry where longer wavelengths of light are far more effective at bigger scales. However, the array of molecules that absorb light in this region and can effectively deliver it as chemical energy are vanishingly small. Our group is investigating how cheap, abundant, non-toxic main group elements can be used to do just that. Here we are able to work hand in hand with experts in photophysics and computational modeling to help rationally design new catalysts to not only replace these rare earth counterparts, but also deliver new chemical reactivity.
I'm Giacomo Crisenza, and here at the University of Manchester, I am a lecturer in net zero catalysis. My research here at Manchester focuses on uses feedstock chemical and converting through electrochemical methods into value-added molecules that can be embedded in our everyday materials, medicines, and agrochemicals. Chemistry, brightly colored gases, exploding metals, corrosive liquids that burn through concrete, and poisonous wild spiders extracted from the depths of the ocean floor. This is why I became a chemist. You can see chemistry, you can touch chemistry, you can smell it, and you can taste chemistry. For it underpins almost every aspect of our everyday lives in ways that to this day still amazes me. But while everybody has heard of chemistry, not many people really know what chemists actually do and what chemistry can actually do. In the 1960s and 1950s, chemistry had hailed the solution to combat the growing needs of an eager and excited post-war world. Innovative synthetic materials, life-saving medication, pesticides bringing down the cost of food, and silicon chips driving a technological revolution as forging a path towards a brighter future. But in the 20 years that followed, we became all too aware of the responsibility chemists bear also for organic contamination, greenhouse gas emissions, ocean acidification, ozone depletion, climate change, and plastic wastes. Today, chemists face a different set of demands in light of an ever-expanding and aging population, and how this affects the treatment of disease, the global food and water supply, the disposal of waste, and the production of energy. As synthetic chemists, it's our job to develop new and more sustainable ways of accessing unchartered chemical space. So, what does really this mean? In its simplest form, we come up with new ways of making functional molecules that can be embedded in your everyday materials, medicine, and agrochemicals. Hopefully this short lecture would have inspired you that a new sustainable future is possible. And if you are a young chemist out there and you want to be part of this new, more sustainable revolution, there is no better place than Manchester for doing this.
Hi, welcome back to our Q&A section. My first question is going to be, can you explain more what photochemistry is?
Yeah, sure. So photochemistry is a branch of chemistry that study reactions that are driven by light absorption. So in this case, you don't need to heat up your reaction mixture, you just need to shine light on it at a specific wavelength, of course, depending on the reaction. And this reaction is occurs only if you upon light absorption. So, for example, specifically what happens is that upon irradiation, one of the molecules that you have in your reaction mixture absorbs light and reach an excited state. And in this excited state is a completely different thing compared to what was before absorbing light, right? And acquire completely different reactivity. Right? So you can have the same molecule, heat it up, have one reaction, or shine light on your reaction mixture and obtain a different outcome. Okay? So this is what we study in photochemistry. Specifically, what we're doing is using this reaction to synthesize new molecules, right? So for example, we want to have a more sustainable way to synthesize a precursor that can be of an agrochemical or of a
healthcare product or of an active pharmaceutical ingredient, right? And we want to synthesize the small building block to then be put in a more complex molecule. And we design new processes that use light instead, for example, of like a transition metal or of very high temperatures or very harsh conditions to make this reaction happens. What we use in these cases is, so as you need like a molecule that absorbs light, you need a molecule that is colored. If you want to use visible light, but you can also use wavelengths that our eyes doesn't see. So for example, in the UV spectrum, and although the problem in this case is the majority of molecules absorbs in the UV spectrum, right? So you can have also siren activity. So what we use, what I think Aaron showed, like said in the video, is that sometimes we use like metal complexes like iridium that are very colored. So you can use visible wavelength for making iridium absorb light and do the magic, let's say.
Mm-hmm. So this method seems a lot more efficient than other methods. What are the limitations towards it?
The limitation so far, because of course, like, you know, where people are currently researching it, can maybe be scalability in the sense of an industrial process, so that like in our labs, it's easy to set up this reaction. You take one lamp and you put on your reaction flask, but imagine that you need to irradiate an entire massive tank or like an industrial vessel, right? So we want to, perhaps the technology needs to improve in this sense.
Just picking up from what Giacomo said there, you mentioned the use of something like an iridium catalyst. Now, iridium is actually space dust. It doesn't naturally occur on Earth. So we have a very small amount of this available, and it's very expensive, very energetically challenging to extract it from all the other metals. And so we want to really move away from this, especially geopolitically, in order to have more sustainable catalysts that we can use to drive these reactions. And so a lot of research is focused on how can we take that reactivity that iridium gives us, but translate it to more earth abundant and potentially even moving away from metals altogether to drive these very powerful chemical reactions.
So if we were to move away from metals, what alternatives do you think could be used, or is it just really anything that could be used?
So some cutting edge chemistry involving, say, iron-based photocatalysts, as well as just organic molecules themselves. So a lot of dyes. I mean, you're wearing a denim jacket there. I mean, denim, the indigo in that, strongly absorbs light. How can we use those sort of highly coloured organic dyes and molecules to do chemistry instead of just be a colour? That's something that we look at as well.
This is again linked to the previous question. What are there risks associated with large-scale use of photochemical systems?
In this, I'm not sure if there is risks.
I mean, in the sense of that any chemistry does have risks, but I guess when you heat something, there's pressures involved in that, high temperatures. It can be dangerous. With light, all of these reactions we do at room temperature and sort of room pressure, and we're taking the reactivity that the heat gives you and use light instead. Now, as Giacomo pointed out, that can have issues around scalability, and also blue light can be damaging, but overall I think it's widely considered to be a lot safer, a lot more scalable, and a lot more sustainable moving forward.
Could photochemistry and radioactive materials, or nuclear engineering, be combined to deliver a more climate-friendly future and serve as an energy source that genuinely has zero net emissions?
Blimey.
Yes, perhaps he's a bit of outside of our expertise on nuclear engineering, or...
Here at Manchester we have a Centre for Radiochemical Research, and I guess it may be tangentially linked, but some of the work that they do is to look at how complexes of uranium, so really waste products that no one wants anything to do with, can we actually turn those into viable catalysts to do chemistry? And actually some excellent work from the little group here has shown that actually is possible.
Yes,
but whether or not we could use that to do energy production, that's something that we might have to get back to you on.
Yep. How can synthetic plastic fabrics be disposed of better or more efficiently?
There are actually research done that use photochemical methodology to depolymerize these plastics. So you can take your old PET bottle and making a fine powder and put it dissolve it in a solvent, and with a photocatalyst, what Aaron was saying before, you can trigger one of these reactions that takes the long chain of your polymer and then makes it back to the monomer that you can use for something else.
How efficient are these processes, and how viable are they to happen on a larger scale?
I mean, so far they are efficient. I'm not sure. They are probably looking into making it in larger scale. So I'm not sure if the technology is there yet, but they are efficient on a lab scale.
Yeah, some real cutting edge advantages using black plastics
True. Yeah.
that absorb light. So it's actually a thermal process, but they're just capturing all of the energy and the heat. And I think some of this research there's some work in Princeton that's really excellent on this, using sunlight to capture the heat, and then it gets so hot that it basically turns itself, as Giacomo said, back into the monomer that you can re-distill out of it. So it almost completely goes from being a plastic back into the monomer. It's really
out of your coffee lid.
Out of your coffee lid.
The coffee lid, what they get back is styrene, which is the monomer of polystyrene, the one that you use for packaging. So you can take your coffee lid that you would otherwise throw away, steal the monomer that you can use in packaging, and back again in the cycle.
So yeah, I think there's definitely a really bright future in that area of research.
Yeah. Next question is, given the high energy demands of the Haber process, what are the most promising catalytic or process innovations being explored to make ammonia production more sustainable?
Yeah, that's a great question. So, I mean, in contrast to the Haber-Bosch process, which, as you know, is incredibly energy intensive, nature, as always, has come up with incredibly ingenious ways of solving these problems, and nitrogenase enzymes are able to fix nitrogen at room temperature under very mild conditions. Now, we actually don't quite know how these enzymes work. It's still quite complex, but what we do know is that they have these metals or organometallic clusters in them, which are very reactive. Now, for over 40 years we've known about these, but still, as chemists, no one has really come up with a way of solving this problem of how do we turn what nature can achieve into a viable process that we can use. And part of the challenge for that is that all of the molecules of ammonia that come out of this process require the nitrogen to be coordinated to a metal. But not only that, we need to put an electron in order to break that very strong nitrogen-nitrogen triple bond. And that electron has to come from somewhere. And photochemistry is actually one of the most promising avenues of research in here, because what we can do is we can take this strongly reducing system that we can access with light in order to drive that reduction. And that's definitely looking, whether or not we'll see that in the next 10 or 20 years, I don't know. Some of these things are as much of a chemical engineering problem as they are as a fundamental chemistry problem. But there's definitely a lot of research, and it's a very hot area right now.
Our next question is a bit more general. What are the career paths or specialisation you can do after studying chemistry in university, and is there any advice you would give to students who would want to study chemistry?
Yeah, sure. There are. So other than doing research or working, for example, in a pharmaceutical company, in a material company, yes, we have many colleagues actually that became patent attorney, for example. You can become a teacher as well. Many actually choose this path. You can work on science communications as well. It's like a very taken career path. And any advice for studying chemistry is my advice for anyone joining the university is that you should really be passionate of what you're studying, right? Because this is the best way to move forward, right? So if you feel that you're passionate about chemistry, the thing is chemistry is a very big field, right? So you can be passionate about synthetic chemistry, but you can also be passionate about computational chemistry, physical chemistry, inorganic chemistry, biochemistry, right?
Yeah.
So there are lots of different paths that you can explore within one subject.
Chemistry is, considered by many to be one of the most central sciences. If you go, you can go into the smaller scale in physics, you can go into the more biological aspect of biology, but chemistry is everywhere, all around us. We're sat on these these sofas made of material that, fundamental chemistry behind polymers. And we interact with it, although we don't think we do. We interact with it at every stage of our life, be it from the toothpaste in the morning to your shower gel to the food and the packaging, just everywhere. The clothes that you wear as well. I mean, fashion and the technology that goes behind that is enormous. So chemistry, is one of the most fundamental sciences that you can study and then apply to any other field that you want to.
You move for a chemical reaction, you see for a chemical reaction, right?
And it's fun. Chemistry at the end of the day is fun. Where else do you get to throw, reactive metals into water that explode or coloured gases,
Oh, also you guys
we
do have
with
more
the,
fun
with
experiences.
the CRA form from Milton Safety.
Yeah, exactly. But we do have fun.
So these questions are more for Jen now. Okay. Can you tell us a little bit about who you are and what you do at the university?
Oh gosh, I wasn't expecting that question.
Yeah, just a really big one.
No, actually, I'm Professor. I'm Professor Jennifer O'Brien, or Jen to my friends. I'm actually a geographer by training. I did my undergraduate now, many, many years ago. So I teach, and it's very important to me that I maintain my time with students in a classroom, and that feeds into my research. So for me, research and teaching are a symbiotic. They flow together all the time. I learn as much from my students as I'm teaching them. But I also work as the academic lead for sustainability teaching and learning, which is a phenomenal job. So 46,000 students, I have to think about how we can integrate sustainability into their teaching and learning. And there's two key bits for me there. One, that we are genuinely integrating. So I try not to use the word embedded. So everyone said we're embedding sustainability. But for me, embedding, you're forcing something in, and it can also be taken away. So we're working to the stage at which all of our learning is almost underpinned with sustainability. So if we remove it, it all falls apart. It's essential to me that it is a prominent part, but also because it's then part of the curriculum, it's accessible. So many of our students, chemists are really busy. You might also have to work. You might have caring commitments. You might be commuting. Want to get to a stage where it's not an additional, it's not an add-on. So we do loads of amazing co- and extracurricular activities, but we're channeling these core priorities of the university through our education. And for me, that's fascinating. So 46,000 students, so I work across the university. I'm actually not a chemist, but so in the morning I could be talking to somebody for whom sustainability is defined as indigenous voices in the Amazon rainforest. And in the afternoon, I could be working with someone for whom it's all about nuclear power. And that's what I love about sustainability at UOM. We take this really interdisciplinary, largely student-led approach to sustainability that brings that all together. So my job is really cool, and I get to work with amazing students, fantastic colleagues, but also reaching out. So we're a civic university. We are very proud of the positive difference that we are making with and for our communities near and far, and that extends to our neighbours as well. So I do a lot of work with GMCA, our Greater Manchester Combined Authority, and Manchester City Council, because viewers might be aware that we have carbon targets by 2038 to hit, to ensure that when we talk about there's no planet B, there is no planet B for human beings. The planet lived a long time before we were on it, and it will succeed us quite a way. But how can we sustain our planet? Well, we have to reduce our carbon budget. And our students work with us to do that. So different ways in which students can affect change with our councils, but also communities further away. So my job is broad, but it's really fun. Yeah. It's really engaging.
On the whole vein of it being a very student-led concept, can you tell us a few ways that students can get involved in sustainability while they're at uni?
Yeah, loads of things, loads and loads, almost too many. How long do we have? So we have a programme called Stellify, which is our leadership award, in which students have different opportunities to get involved, either through their teaching, so many of our modules that are interdisciplinary, so some that run through the University College for Interdisciplinary Learning, and I'm going to shamelessly flag my own course, Creating a Sustainable World, which is available to all, including chemists, all students, 10 credits, 20 credits or 15. So there are ways in which students can bring that into their learning, so additional interdisciplinary units. Increasingly courses, so chemistry is a good example, which is inherently sustainability. We're sustainability driven, we've heard about that today. But I'm really interested, for example, in how we can get sustainability into medieval history or into, they're not obviously green degrees. So increasing those opportunities for students there as well. And then we're doing a lot more applied learning or externally facing learning. So I run this thing called a University Living Lab, where our students can undertake assessment that's been set by external organisations, and it feeds into their day-to-day assessment. We are doing a lot more partner enhanced learning, for example, where we're doing client-based learning, we're working with our communities. We have the most incredible volunteering program where our students are working with communities local, all the way through to global destinations. So they're enhancing their learning by making a difference at the same time. So a whole host of different ways that students can get involved. But also our strategies are built with our students. So if there's anything that our students would like to do and the opportunity is not there, we will work with them to try and see if it's possible. It's not always. I'm yet to find something we haven't been able to do, but we work very close with our students to enable those opportunities as well.
Thank you so much. That's unfortunately all the time we have. If you have any more questions, put it in the chat and someone will come and try to answer your question for you. But thank you all so much.
Thank you.
Welcome.